In this video, we are going to look at how we solve problems that involve straight line motion using the numerical approach. Now, we use the numerical approach when the parameters in the question have been given at different time intervals. Sometimes can be given a question. They can tell you that probably a particle starts from rest, or it starts from a certain point, and after a certain time t, it has moved a certain distance s1. Then a certain time t2, it has moved a certain distance s2. So you'll find that the distance moved here is probably not the same as this, or if they are the same, probably the velocity, the acceleration between the velocity between this point and that point is not the same as the velocity between this point and that point. That kind of thing. We are going to look at examples to look at how it comes out. Now, the whole point here is that if the information has been given to you in that kind of format, let's say you're having after t1 a particle covers a certain distance s1, maybe after t3 a certain distance s3 has been covered. If you've been given the information in that kind of format, it means that you are going to analyze each and every interval. You're going to look at the question in terms of interval by interval for you to be able to get the acceleration, because right here, much as the information has been given to you interval by interval, here we are looking at constant acceleration. So it means that the acceleration is going to be the same. So it means that our main issue here is to be able to find the acceleration. If we are to be able to find the acceleration throughout this whole motion, this straight line motion, then we can get the initial velocity, the final velocity, and so on and so forth. So we will be able to, in this case, we shall be analyzing interval by interval. Let's say we want to find the acceleration. So we'll look at the initial interval from t0 to t1. The initial interval, we will get the average velocity in this initial interval and the average time. Then we shall get to the next interval. We'll get the velocity between this interval and the time. And then now that we have the velocity in this interval, we have the velocity in this interval, and we have the average time in this interval and the average time in that interval, then we can use these two intervals to get the acceleration of this whole straight line motion. Because since we have the velocity and the time, we know that acceleration is the rate of change of velocity with time. So it's a matter of saying that the velocity of this interval minus the velocity of this interval, divide that by the time, average time here minus average time there, we are able to get the acceleration. Let's go through this step by step. Let's assume this is what we've been given, and we've been told we want to find the acceleration for a particle that's moving from this point to that point. So how do we go about this? We are going to consider interval by interval. So let's look at the first interval from t0 to t1. From when the particle started moving from this point, it moved up to, after t1 it covered a certain distance s1. So to get the average velocity here, of course we know that velocity by definition is the rate of change of displacement. So we get the final displacement here minus initial s1 minus s0, divide that by the time t1 minus t0, so that we are able to get the velocity in this interval. And of course the average time in between here is going to be t0 plus t1 divided by 2 to be able to get the average time in this interval. So we've got the information for that interval. So it means you're going to go ahead and get to the second interval, t1, t2. So in this second interval, we are still going to do the same. We want to get the velocity in between this interval because the velocities are not the same. And by definition, from our theory, we know that the rate of change of displacement equals velocity. So meaning that to get our velocity in the second interval, it's going to be s2 minus s1, divide that by t2 minus t1. I mean the rate of change of displacement divided by the time in that interval for us to be able to get the velocity in this interval. After getting the velocity in that interval, then we get the average time here. So it's going to be t2 plus t1, divide that by 2 to get the average time in that interval. Just like we did in the previous interval, we got the average time. Now, from these two intervals, now that we have got the velocity here, the average velocity and the average time here, we have the average velocity and the average time in this interval. So getting acceleration, by definition, we know that acceleration is the rate of change of velocity. So it means that this is going to be this minus that. Velocity here minus velocity there, divide that by time here minus time there. And this is how we'll be doing it. That acceleration is going to be equal to the initial velocity. Acceleration is going to be the average velocity in the second interval, which is v prime prime, minus average velocity in the first interval, which is v prime, divide that by the average time in the second interval, which is t prime prime, minus the average time in the first interval, which is t prime. And we're able to get the acceleration that we are requiring, or that we are looking for. For us to be able to get the initial velocity, we are going to concentrate on interval by interval. When we are using this formula, v is equal to u plus at, if we want to get the initial velocity and we have decided to concentrate on the first interval, it's going to mean that our value of v, the final velocity, will be v prime, which so happens to be the average velocity gotten here, and our value of time in this equation will be t prime, which is the average time gotten in this first interval. If we are to use the second interval, it means in our substitutions of v is equal to u plus at, our value of v will be v prime prime, which so happens to be the average velocity in the second interval, and our value of t that so happens to be t prime prime, which so happens to be the average time we got in the second interval. So we'll do a raft example. A train approaching a station runs 2 successive half kilometers in 16 and 20 seconds respectively. Assuming the retardation to be uniform, find the initial speed of the motion of the train and the further distance the train runs before it actually gets to stop. So here's our summary. That's the straight line motion of the train. A train is approaching a station. It is going to run 2 successive half kilometers in 16 and 20 seconds. So it's going to run 2 successive half kilometers, and we know now half kilometer has got 500 meters. So we have the first half a kilometer, which is 500 meters. We shall use 500 meters. We are converting the kilometers to meters. So this is half kilometer, of course, and that is half kilometer. So a train approaching a station runs 2 successive half kilometers. So this is the first half kilometer and this is the second half kilometer, and this in meters is 500 meters, and this is also 500 meters. So 2 successive half kilometers in 16 and 20 seconds respectively. It means that in the first portion it was 16 seconds, in the second portion it ran for 20 seconds. Assuming the retardation to be uniform, so it means that the retardation, which is negative acceleration, is uniform from this point all through. So find the initial speed of the train. So let's say this is our point A, that's our point B, our point C. They want us to find the initial speed here. And then, so of course, for us to be able to get our initial speed, we need to first be able to know the acceleration, because for us to be able to get the value of u means, or the initial speed, means we are going to use v is equal to u plus at. So we need to first find the value of a. Then when you get the value of a, which is the acceleration, then we are able to get the value of u using specific intervals, as we will be able to choose. So we'll start off just like in our earlier illustration. We shall go interval by interval. So now between a and b, what is our we know that velocity is change, we call it v prime. Our v prime is going to be the displacement. Let's call this if this is displacement at 0, let's call it s naught, or s at a. Then this is the displacement at point B, then this is the displacement at point C. Then the time taken, let's call this the time taken at point A, time at point A. This is the time taken at point B, this is the time taken at point C. So to get the displacement, the velocity, initial velocity here is going to be equal to the change in displacement, which is SB minus SA. Now SB minus SA so happens to be 500 meters according to the question, so it's going to be, let's first write that down, SB minus SA, divide that by time. The time in that interval is TB minus TA, and the time in this case is going to be, so it means that our initial velocity SB minus SA is already spelled out here as 500 meters. Divide that by the time between here and there. TB minus TA is 16 seconds. The time taken is 16 seconds. And of course, 500 meters, divide that by 16 seconds, we shall end up with our average velocity being equal to 125. Divide that by 4. This is in meters per second. So what about our average time between here? Of course, our average time is going to be equal to the time at this spot plus the time at that spot divided by 2. That is TB plus TA. Divide that by 2. And we shall end up with, of course, the time at A, this is when it just started, so it is 0, plus the time at B. The time at B is definitely 16 seconds, because it takes 16 seconds to reach this point, so it's up plus 16, divide that by 2, and we shall end up with 8 seconds as our average time. So that is it for the first interval. So we'll go on and look at the motion between the second interval between B and C, and we are going to do the exact same thing. We get the average velocity in the second interval and the average time. So looking at the second interval, our average speed or our average velocity, we shall call V prime prime, is going to be equal to SC minus SB, divide that by time TC minus TB. That's going to be equal to, now the displacement between B and C, SC minus SB, is already 500 meters. So it's going to be 500 meters. Divide that by the change in time here is definitely 20 seconds. And of course here our velocity V prime prime will be 25 meters per second. So we'll go ahead and find the average time in this slot. The average time we shall call T prime prime is going to be equal to the time at B plus time taken to reach C, divide that by 2. So the time taken to reach B is 16 seconds. Add that to the time taken to reach C, it means from A up to C is going to be 16 plus 20, which is 36. Divide that by 2, and definitely our answer there for average time is going to be 26 seconds. So we've already finished getting our average speed and average time for the second interval. So after getting those two, we can go ahead and now get our acceleration, because the question requires us to find the initial speed of the train, but we can't get the initial speed when we do not have the acceleration. So first we'll get the acceleration. So the acceleration in this case will be equal to, is going to be the rate of change of velocity. So it's going to be V prime prime minus V prime, divide that by T prime prime minus T prime. And in this case, our V prime prime we got as 25 minus V prime. Our V prime is 125 over 4. Divide all that by T prime prime, which is 26. Divide that minus T prime, which so happens to be 8 seconds. And our answer for that, we'll get our acceleration as negative 25 over 72 meters per second squared. That's our value for acceleration. Now that we have our value for acceleration, we can go ahead and find our value of u, the initial velocity, which is required of us to find in the question. But now to get our value of u, you're either going to concentrate on the first interval or the second interval. If we are to concentrate on the first interval, that is between A and B, and we are going to use V is equal to U plus AT, what is going to be our answer? V is equal to U plus AT. if I'm to look at it from A to B, for me to be able to get the value of u, it means my v is supposed to be v prime is going to be equal to u plus the acceleration, and my t is supposed to be t prime. So my v prime, from what I got, v prime is 125/4 right here. So it's going to be 125/4 is going to be equal to the initial velocity u, which I'm looking for, the velocity at point A, plus now the acceleration is what I got earlier. My value of A is negative 25/72. So it's negative 25 divided by 72 times time t prime. Now the t prime I got earlier as, my t prime is 8 seconds. Actually, this is t prime. It's 8 seconds. So when we make use the subject of the formula here, we shall end up with 1,225 divided that by 36, and this is in meters per second. Now this is, if you are to convert this to decimal point, it is approximately 34.0278 meters per second. That is the initial velocity, or the velocity at point A, and that makes us to get the initial speed or the initial velocity at point A, which is that. We've already answered that. Solve this using our first portion. Now we can still get the same answer using the second part of the motion, and in this case, if we are to use the same formula, v is equal to u plus at, v is equal to u plus at, but in this case we say that we want to find our value of u when we are using B to C, that is from B to C. It means that our value of V in this case here is going to be V prime prime, because we are using the second spot, is going to be equal to U, the one you're looking for, plus the acceleration, which is the same all through, times T prime prime, the average time in the second slot. So it means that the V prime prime average velocity from here is going to be what we got. Our v prime prime, we got 25 meters per second, so it's going to be 25 meters per second is going to be equal to the u we are looking for, plus our acceleration. It is still going to be the same, negative 25/72 times t prime prime. Now our t prime prime, from our earlier calculations, we got it as 26 seconds, so it's going to be 26 seconds. And of course our value of u there is going to be 34.0278 meters per second, just like the way we got this one. So you can either get the value of u either using the first portion or the second portion of the motion. We go ahead and find the second part of the equation. They're asking us to find the further distance the train runs before stopping. Now we realize that this train has been retarding. So it means this train has been retarding. So if this train has been retarding, we are being tried to find the further distance the train runs before stopping. So it has been running from this point, it has reached up to that point. Now how much further is it going to run for it to reach at a point where its velocity is 0? Because when velocity is 0, the final velocity is 0, that is when it stops. So what is this further distance? We are looking for this. So it means that we just need to find the whole of this distance. So we have the initial velocity, we have the final velocity being 0, then we have the deceleration. So we need to simply find the whole distance. Then when we get the whole distance, then we subtract it from this distance, so that we're able to get the further distance it has to travel before it comes to rest. Looking at our diagram here, we have the whole of this. From here, our initial velocity u, from our earlier calculations, when the thing started moving, we got it as 1,225/36 meters per second. From our diagram, we're able to see that getting to this v is equal to 0. To get this extra distance, we have an initial velocity there, which is 1,225 divided by 36. Of course, this is equivalent to, or approximately, 34.0278, but I prefer to use the fraction form of this so that I do not tamper with the accuracy of my calculation. That's the initial velocity. We already got our retardation as negative 25/72. This is in meters per second squared. This is our initial velocity, retardation. So we know that our final velocity when it comes to rest has to be 0. So our final velocity is 0, and our task here is to find the whole distance so that we are able to get the further distance it travels before it comes to rest. So we need to get our value of s. So if we are to use our third equation of uniform acceleration motion, which is v squared is going to be equal to u squared plus 2as. Our v squared final velocity v is 0, so it's going to be 0 squared is going to be initial velocity u squared, which is this. I'll plug in the fraction to preserve my accuracy, plus 2 times the acceleration, which is minus 25/72, times the distance traveled, which is s. Of course, here when I make s the subject of the formula, I will end up with my value of s as 1667.36 meters. So it means that it is 1667.36 meters moved from this point to that point, to the point when it comes to rest. So the further distance covered means it's this whole distance minus the 1000 meters. So the further distance covered, right before your screen is another number that you can try out and see if you'll be able to get the required answers. For Roman 1, the acceleration, I expect to get 0.27 meters per second, and Roman 2, the velocity with which it passes A, that is the initial velocity, I expect you to get approximately 0.67 meters per second. And this brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.